Good morning. This is DI504, Foundations of Deep Learning. After the midterm, we had one lecture the previous week. It was about an introduction to sequence models. And if you remember, and if I remember correctly, we have made a gentle introduction to the concept of a sequence. What is a sequence? What is not a sequence? Why convolutional neural networks we've learned so far, which was a type of neural network from the family of feed-forward neural networks, if you remember, why they were not suitable for sequence models we have discussed. And we've talked about the concept of memory, concept of a varying length data. And we said that the usual feed-forward neural networks, which are convolutional neural networks or artificial neural networks, those usual fully connected layers of neural networks, they were not compatible with dealing with this sequence models, we said. And we made an introduction to recurrent models and recurrency in a neural network. We talked about what makes a network recurrent. And we said that when a neural network has connections from its output to the input, like a feedback connection of a control system, we said that it was a recurrent connection. Recurrency is feeding yourself in any system. I mean, recurrency, so you are all graduates of some important field. So I'm sure some sort of recurrency was modeled in some of your lectures. If you're coming from electrical engineering, it's obvious, it's control engineering. But even if you're coming from social sciences, recurrency is something that you feed the output to the input. So the output reoccurs in the input. And we've discussed how recurrency works, how it affects. We've seen that recurrency creates states in a network. And when you can create states in a network, just like the states of a finite state automata, you can create memory. You can create the ability to understand the dependencies, the relations inside an incoming sequence, the elements of an incoming sequence. That's why we said recurrent neural networks were suitable for modeling sequences. Then we talked about what sequences were in terms of their input-output relations, if you remember. So if you have single input and many output, or many input, many output, what happens when you have delays? These are important concepts because they are modeled in platforms like PyTorch and etc. And we have given examples about use cases, problem definitions, sample problem definitions about these different input-output types for sequence problems. This week, we are going to continue this problem. We're going to continue talking about sequence models. And we're going to talk about an important design. Some of you must have heard of it. It's called the Lstm. It is short for long short-term memory. We're going to understand why it is important. But just like the previous week, we are going to do this very quick. We're going to do a fast scan on this, okay? Because sequence modeling is a vast concept on its own. And as you all know, I have an advanced level deep learning course for sequence models in multimedia, which I'm lecturing this semester. I mean, if you're taking this course, you're not taking that course because that course requires an introductory level deep learning course. So if you want to continue that subject, you're welcome. I'm going to lecture that course again. The thing is, since that's a vast concept of its own, this is sequence modeling, we will have to just pass it a bit quickly. And actually, this is what happens in an introductory level deep learning course, as far as I see. I mean, I checked many of the online deep learning courses, and for most of them, this subject, recurrency, LSTMs, and how they can be used, how they can be optimized, can only be a little part of the introductory level deep learning course. This will be the same for this course, but I think introducing them is still important. That's what we are going to do. We're going to first talk about Lstm, which is a handcrafted RNN architecture. We're going to understand the beauty behind it. Then we'll talk about NLP. Again, once again, NLP is an advanced concept, which is a course of its own. And again, at an introductory level deep learning course, NLP is visited with a very limited scope. That's what we are going to do. However, still, understanding the Lstm... gelmiş miydim? Nasıl yapalım? Arkadaşlar, classroom lecture varmış da. Şimdi kayıt da başladı. Ben bunu silerim aslında da. Nasıl yapalım? Sorry about that. Apparently there's somebody for the classroom. What I'm going to do is I'm going to cut the first hour a bit short. I'm going to give a break and I'm going to carry us to the classroom while he's going to listen to us in his laptop. I'll continue, so nothing is, don't worry about it. What I was saying is deep NLP is also a concept of its own, vast concept, and beyond the scope of this course, but we are going to make an introduction because many of you are interested in the field. And as DI students, I mean, you are not all DI students, but in this DI program, we have a very, very nice course about NLP. I hope that it is going to be an introduction to it as well. Okay, so I'll try to do my best to cover the important concepts a bit fast, but I think they will be good introductions to you. Okay, so I'll be using the figures in these slides. I'll be using the figures from a famous guy. This is Michael Fay. He's famous because he's preparing videos of AI architectures from, I mean, very important, from LSTM to transformers in his YouTube videos and blogs, and he's doing a fantastic job. I'm borrowing his figures. Watch his YouTube video. It will help you a lot. So I'm going to use his figures as well. So the thing that we've seen in the previous week was a recurrent neural network. And in a recurrent neural network, we have an input, and we also have the hidden states as the inputs. If you remember the figure, that figure can be depicted as this way as well. So imagine this is the input coming in. And here I'm having the, let me get my pen. So let me get my pen. So this is the input X coming from here. And these are the hidden states. So this is a sequence of vectors. So this is a sequence of 3 by S vectors, where S is the sequence length, 3 is the feature length, because I have got 3 values. So I'm feeding a sequence of S length vectors, 3 long vectors, S number of. The first one is X, let's say it's X0, and the last one, let's call it XS plus 1, X minus 1. I'm feeding it from the input. And I'm also feeding an initial value for the hidden states. And we said that it's conventionally all zeros. So this is what happens here is a concatenation. Remember, A and X were concatenated. They become one vector. And I feed that to an actuation function, which is inside it, there's a weight plus bias and an actuation function, which is this part. And I have the output, and which is, if this is A0, this is A1, which is being fed to the next sequence element, so which is X1. So take, in this case, A1 and X1 are concatenated, multiplied with the same matrix. Matrix doesn't change because these are the same recurrent nodes. This is an unrolled in time representation. And I calculate the new one, which will be A2. So that was the story, if you remember. This is how this guy puts it in a figure, which is quite elegant, in my opinion. So this was RNNs in a nutshell. RNNs have been found almost like 50 years ago, the idea of recurrency in a neural network. I mean, the idea of recurrency was already there because of control theory and stuff, more like 80 years or 100 years. But the idea of using a feedback connection on a neural network is kind of 50 years old. However, when people start working on these RNNs, although they promised a very strong potential, they realized that it was very difficult to train them because of a problem called the vanishing gradients problem. We're not going to delve into the details of this, but actually we delve into the details of that problem in the advanced sequence modeling course. So if you're interested, I invite you to that course once again. So because the gradients vanished when we were trying to train these recurrent neural networks, especially when we had very long sequences. Actually, this vanishing gradient problems we are going to talk about in the following weeks, because in the following weeks, I'm going to be talking about some special architectures of deep neural networks like residual nets and etc. And there we're going to realize that as the depth of the network gets deeper and deeper, it is difficult to train it. And there are solutions for that. And actually, that problem is also related to vanishing gradients. And you will understand why a long sequence will be difficult to train for an RNN in that case. But don't worry about it right now. What I'm just telling you is the vanilla RNN, the simple form of RNN, was hard to train when we had very long sequences. And actually in 1997, actually 1996, the first time they applied for a conference, a guy from Germany, his name is Jürgen Schmidhuber, he's a famous guy, come up with a design for a recurrent neural network, a specific architecture, which is called the long short-term memory. And some advances on that architecture continued even today in 2014. There was another one called GRU, which is a kind of an extension of Lstm, which is a slightly different version, but doesn't matter. So like 20 years ago, we had a nice design of an RNN, which could train longer dependencies. Why? So RNNs, while processing the data, passes this hidden state, sometimes denoted as A, if you remember, I talked about this, sometimes denoted as H because it's a hidden state, to the next step of the sequence in this unrolled in time representation. Remember? The hidden state acts as the neural network's memory, because as we feed the input from here, the input might change because it depends on the outside world. And that's the input. We don't control it. However, as the input is being fed to this recurrent node, because this node and this node are the same thing. Remember, this is an unrolled in time representation. They are not two separate nodes. This is the same node. We are trying to present that in a way that when you're feeding different inputs, we can depict it, because when you're drawing something, you cannot draw an animation. So this is the first time instance. This is the second time instance. This is the time dimension. So this hidden state acts like a memory because it evolves in time. States change. So if you know what state will correspond to, that would be the state that you're using. It holds the information on previous data network as seen before. Okay. Actually, just like I said, we had a problem with this RNN to be trained when the sequence got longer and longer. So this is in these slides, you're seeing the kind of summary that I've been doing in the last couple minutes. So we concatenate them and we feed them to this gate where there are some weights and an activation function. Good. Vanilla RNNs traditionally use 10H as the activation function because they wanted the output to be bounded between -1 and +1, because they didn't want to explode, get larger and larger. Imagine this is not bounded. It can take values. In that case, when you feed a long sequence, as a result of the incoming hidden states and inputs and hidden states, the output would grow, the next hidden state will be larger, hence the next hidden state will be larger, it will explode. The first designers of these recurrent neural networks, they wanted to be between -1 and +1. That's why they use this 10H function. Today, the story is a bit different, but still 10H is an important function for recurrent neural networks, especially for Lstm. So having these ideas and seeing that it was difficult to train recurrent neural networks with longer sequences, Schmidt-Huber come up with an idea of a unit, architectural unit, handcraftedly designed as a recurrent neural network. The problem of vanishing gradients was a similar problem that the residual nets had. I'm going to be talking about this in the following weeks. But the answer to this problem was Lstm. How we could solve the vanishing gradients problem, how we could solve the difficulty in training long dependency, long sequences. So this is an Lstm. If this is an RNN, where X is the input, H is the hidden states, where this is the concatenation of two vectors, this is the 10H function, and this is the output. If we could put it this way, graphically, this would what Lstm look like. This is the Lstm. So in Lstm, the difference is, let me show you. We have two types of hidden states. You see there is a hidden state vector called A here, or in Michael Fee's figures, it's called H. Doesn't matter. In Lstm, you have two separate types of hidden states. The first one is A, and the second one is C. C is also called the cell state, and A is also called the hidden state, just like we did for the RNNs. Actually, I'm going to tell you the thing that I should be telling in the end, which was the moral of the story. The cell state is kind of a hidden state which holds the long-term memory. And hidden state A is a type of memory which holds the short-term memory. That's why this guy is called the long short-term memory. So what happens is, it's just a simple bunch of networks. You have X and A being concatenated, being fed to a sigmoid gate. And you have an output at the sigmoid function. Then the same thing is fed to another sigmoid gate. In all of these gates, we have separate weights and biases. I'm going to show them. By the way, the cell state coming from the previous time instant, because this is a hidden state, kind of hidden state, separate two hidden states. It is being multiplied element-wise by the output of this sigmoid. Because if this has L elements, the output of the sigmoid gate also has L elements. And it continues, it's being shaped. So we're going to go over these. This is a handcrafted design for a purpose. What is that purpose? I'm going to be showing you in the following slides. Actually, although it seems a bit, I don't know, complex when you first see it, these pieces have meanings and they also have names. For example, I'm going to get back to those slides, don't worry. The first part of this network is called the forget gate. The second part is called the input gate. And the third part is called the output gate. And they all have purposes. I'm going to talk about those purposes, but before I talk about them, I'm going to give an early break so that I could move to the classroom, and those who came for the classroom will be able to watch the course in the classroom. So let's say past 10, okay? See you in past 10.